So for our final talk today, some of you were involved in a group I got together maybe a year and a half ago about data. You know, a lot of data flows into the building, but how easy is it to get at? And I don't know if Tobin is still here. I remember he was one of the initiators of me wanting to get that group together, because he was just like, I want this data. I know it's in the building. How do I get it? And that group met, and you know, we didn't do anything. Except I learned that there were five A's in data, not two. There's access, there's assemblage, there's analysis, there's artistry or visualization, and then there's archiving. And I think we heard from Nadia. She was really dealing with that assemblage and analysis type approach of dealing with data. But there's a whole big umbrella of how do you do that, and it's a challenge. And so I thought it would be interesting if we found somebody who maybe could address the vision, if you will, of where we might want to be 10 years from now or 5 years from now. In the sense that if we know where we want to be in the future, maybe we can work together and get there. And I'm not saying that whatever Liam is going to say is where we're going to be. I just thought this would be an interesting way to start off a conversation, because there's no doubt in the next 5 to 10 years, it's all going to be about data. Whether it's real data from observations or fake data from models. Being able to get at that, being able to get at that data easily, to assemble it in a way that we want to use it in terms of different data sets, analyze it, visualize it so we can see it, and then put it away for others to access. It's going to be really important. And so with that, Liam's going to tell us something.
Thank you, Steve. I know how to fix the PowerPoint problem on your laptop, by the way.
Oh, you do? What's that?
Anyway, so Steve wanted me to talk about trends in large-scale data processing. I may or may not talk about what he just said, but let's see how it goes. So, a lot of you know who I am, but let me just make sure that everyone understands my perspective. I've mainly been working in my career on LEO satellites, polar orbiters, and in particular images. So, for the last 20 years or so, working with Terra and Aqua, in particular MODIS, but in the last 5 years, thinking more about the new generation of imager on SUMI NPP and JPSS, which is called VIIRS, and on that project, that's the NASA PEAT that we have here at UW, and my experience with applications running on systems as small as an iPhone and as big as our S4 HPC system that we now have here at Space Science. So, this is just a combination of things that I've seen recently in the last couple of years and things that I think are going to happen in the next 3 to 5 years that I think we ought to be aware of. So, why do we need large-scale data processing? And by large-scale, I mean processing multiple years of global data, satellite data at one time. Well, you might have some enhanced calibration algorithm. Let's say for your AVHRR, you've improved your solar calibration in the visible channels. You've improved some retrieval algorithm for doing, let's say, cloud retrievals, and you want to apply that to historical data to come up with some sort of climate data set. You might take it a step further and have one retrieval algorithm, so one set of science code, kind of like a GeoCAD, that you want to run on multiple sensors over a long time period. And it could be, you know, images like VIIRS, MODIS, and AVHRR, for example. And ultimately, you might want to create some sort of time series, whether it's frequency of high cloud, incidence of wildfires, you name it, SST. You want to create some long-term record of satellite data. And it seems to me, maybe I'm wrong, but that's one of the areas that there's a lot of payoff right now. I mean, we've got the data, we've got the sensors, we've got the systems that can analyze it, making those long-term data sets and drawing some inferences from them is where the fame and fortune is to be had. So, just some of the trends, this is more like things that I see happening right now that we're doing that I think are relevant. And this is some statistics on what we actually have in the center. And I got some help from Jerry and Scott Nolan and other people to put these numbers together. The data center right now in 649 hosts about 4,000 CPU cores, which isn't really a huge amount, but it's pretty significant. And more importantly, about 85% of the floor space in that room is taken. So there's a finite amount of space where you can put computers in that room in 649. If you haven't been up there to have a look lately, I encourage you to go, because it's changed a lot since the days when the IBM mainframes were in there. There's several different clusters you might have heard of, including S4, Zara, many people will be familiar with. Pete has a cluster as well. And there's also on the order of about 220 individual Linux servers that are housed in 649 that are doing processing, dedicated processing of one form or another. So a lot of computers. The clusters, there's a couple different kinds. There's clusters like Zara or the P cluster, which we call high throughput, designed to run a lot of jobs at one time and process a lot of data at one time, typically satellite data. The other kind of cluster is what we call high performance, and that's what S4 is. So that's running a few jobs at a time, but each job does lots and lots of computations, uses lots and lots of memory, and numerical weather prediction, WRF, MM5, GFS. Those are the examples of jobs that you'd run on a HPC system like S4. And by the way, all those systems take power and cooling, and those are finite resources. There's been a lot of upgrades in the data center in 649 over the last few years, but at some point you're going to run out of either power or cooling, and you have to take out some of your old systems in order to put new ones in. You can't keep expanding them forever. Just to talk about some recent benchmarks of how fast a system can reprocess data, and these are examples from the Peak project, which I'm familiar with. We did a job for Andy where we reprocessed 33 years of AVHRI GAG data, and it took about 7 days to run that data set, which is a processing rate of about 1700 times real time. For doing other data sets like VIIRS and CRIS, we've recently shown we can do things like SDR or level 1B calibration processing at a rate of about 100 times for VIIRS and 200 times for CRIS, and we've run the NOAA retrieval algorithm that was spearheaded by Andy at a rate of about 45 times real time. So those are the sort of processing rates that I think you need in order to do effective large-scale data processing. And we've done some of that already, but we're not really doing it routinely or operationally. And I think that's where we're going to need to go. So trends in data volume. I was actually surprised by some of these numbers myself, but let me see if we can scare you or shock you. Data center holdings right now, so physical disk space in the data center is now approaching 4 petabytes. And just to calibrate ourselves, let's remember that a petabyte is 1 million gigabytes. Okay? So we've got about 4 million gigabytes of storage now up in the data center in one form or another. Now, it's being used for different purposes, some for archiving, some for processing. This is including all the systems in that one room. That's a significant amount of data. I don't know about the rest of you, but I remember back in about 1988, 89, Bob Fox used to send out these, was it Fox's Folly? And it was actually a printed thing that would come out like on orange paper. And I remember the one that came out that said we now have 20 gigabytes of storage available in the data center. And what a fantastic advance this is going to be and enable all this great science. So we have advanced since then. Just the GOES archive. In other words, probably strictly speaking, that's GEO, is growing at about 50 terabytes per year. When GOES-R goes into space, and that's just GOES-R, it's going to grow at an additional 125 terabytes per year for each GOES-R-like satellite. Our PEAT archive, which has been running only for the last year, is growing about 350 terabytes per year. So we're already starting to, we have long-term data sets in-house, particularly the GEO archive, which is 25 plus years. But you're getting high spatial resolution, high spectral resolution, high temporal resolution, and this problem is not going to go away. Furthermore, for the stuff that we need to do, processing that data, running retrieval on it, calibrating and navigating, whatever it is, that data's got to be relatively close to your compute servers, close in a network sense. You've got to get the data to your compute server so the CPU can do something with it and then store it again. So let me just show you this quick plot. This is the PEAT archive growth for the past year. So on the x-axis it's time, showing you the last year since SUMI-NPP went into orbit, and the growth of the PEAT archive since then. So it's now at a total of 750 terabytes. By way of comparison, the GEO archive, including all the GOES satellites, total over the history of all those satellites is about 700 terabytes. So the peak archive has been increasing at a much faster rate than the geodata. So trends in software. And this is just some observations that I think are probably relevant. Everybody nowadays pretty much is using 64-bit Intel Linux. You know, if you were around here 15 years ago or 20 years ago, it was all SGIs and Suns and Solaris. That stuff is all gone. It's all gone at the loading dock. In the case of our big SGI that we bought for the Modus project, it ended its life infamously outside a frat house, I believe, on Lake Street. The UW-Madison police went and said, "Do you want this back?" And we said no. Somebody took it off the loading dock when it was going for exits. Grid engine for running jobs. A lot of the functions that we do, at least on the Pete system, in fact all the functions we do on the Pete system, depend on a relational database, and for that it's PostgreSQL. Python for scripting. If you talk to any of the comp sci folks around today that I work with, if they're going to develop some scripting infrastructure or what have you, it's Python. That's it. We have a lot of experience now with large file systems and high-performance file systems. So either storing a lot of data on a system that you can grow from 100 terabytes to 200 terabytes to 500 terabytes, or that you want to read and write data really quickly on, like you would on S4. There's a couple of file systems now called Gluster and Luster that we have a lot of experience with. And then the usual suspects for algorithm development, including MATLAB, C, Fortran, and IDL. But what I wanted to convey to you is I've gotten a distinct sense, and I think a few other people as well have gotten this in the last year or so, that talking about MATLAB, for example, it used to be the case that people would say, well, MATLAB's okay for developing a test or a prototype, but you can't deploy that operationally. By God, the MATLAB people, MathWorks, they've had a lot of incentive to speed up the guts of that system for financial modeling, for doing analysis on Wall Street, and the internals of that thing are now really fast. And I'm convinced that you can develop an operational algorithm that's fast enough in MATLAB. And there's a lot of benefit to doing that because that code is easy to understand. You can write a retrieval algorithm to do a physical retrieval or calibrate hyperspectral data in about 100 lines, whereas it might take you 1,000 lines or 2,000 or 5,000 lines of C++ code. Plus a science developer can look at that code and see exactly what's going on. And that's a good thing. And things like subversion and track for source code management. So I don't think any of this is going to change radically in the next 3 to 5 years, but we're going to concentrate more on just the software part and the algorithm part and less on the hardware, where it is, how many cores there are, etc. We're going to worry less about that. I'll talk more about that in a second. So let's talk about a historical data processing paradigm. Typically in the past, and by we I mean CIMSS and ASPV and Space Science, would develop algorithms, they'd implement them in software, they'd test them on data, they'd refine them over time, and they'd send them off to NOAA or NASA, where they'd be run operationally. And I have a bit of experience doing that with NASA, delivering algorithms to them. You fight back and forth, it worked here at UW, but it didn't work at Goddard. Whose fault is it? Well, it's probably Goddard's fault, but you've got to help them anyway. And they implement the software in their own system. Some system they bought from Raytheon or from some other big company that charges $500,000 per person per year. So it's got to work in that system. They might even go and rewrite your code that you spent hours and hours and hours developing and crafting. They'll go and rewrite the darn thing anyway. So now you don't really know what's happening inside it. And furthermore, they decide if they're going to reprocess, it's on their schedule. So you can't say, well, I delivered you the code last week. When are you going to start the reprocessing? Oh, it's going to be another 15 months until the rest of the groups deliver their code. And that schedule, that milepost, keeps moving out into the future. So, for example, with reprocessing of Modus, is something I'm familiar with. For example, the Modus Ocean team have got it. They reprocess their data set, the historical data set, once or twice per year. And they're actually pretty good about doing that. They get it done a lot more frequently than other groups do, and they've been very successful. The Modus Atmosphere and Land teams, on the other hand, over the 12-year lifetime of Terra, they've done a total of 5 reprocessings. And they've been talking about the sixth one, the so-called Collection 6, for about 3 years. They've started it, but they're not quite finished it. The land algorithms need more work, blah, 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 blah. It takes forever. And we have no control over when or how they do those reprocessings. There's no reason why they couldn't do reprocessing every 6 months, okay? Other than it's just too hard politically to get all the groups together and get them working together, get everything organised. We could do things like that here, and I think we will. So let's talk about a new data processing paradigm. I think that CIMSS, ASPB and Space Science should be a community hub, a community centre, a community resource for things including algorithm development and refinement, which we've always done, but also for doing operational, real-time, global forward processing. So all the MODIS data all the time, all the GOES data all the time, all the MediaSat data all the time, daily. And we do quite a bit of that right now, as many of you are well aware. However, that we also have the capability to reprocess any of those data sets, the full mission archive, when we think it's needed, because there's a significant algorithm update, a significant new capability, and furthermore, that we provide the distribution, the search, and the order for those data sets, like a NASA DAC would, or a NASA MODAPS would. Because I think we can do it better, but we can do it better, we can do it, the same functions that they do at those DACs or MODAPS, like a GODD, but we do it here. And I'm actually convinced we are going to do that in the next 3 to 5 years. So why will it be better? Well, the first thing that's going to happen is there will be close cooperation between the people that develop the algorithms, the science folks, and the folks who run the algorithms really efficiently on lots of data, the computer science folks. And I've seen on the PEAT project over the last couple of years how productive that relationship can be. Rather than, you know, the science people are all here at UW, or they're at University of Maryland, or they're somewhere else, and they'll have to send their code off to some set of contractors at Goddard or NOAA. I think that can be a really effective way to get those algorithms running well and running efficiently. You can test new algorithms quickly on large data sets. You can see the impact that a change would have on a long-term global data set. One thing that's difficult to do, I've found, if you send your code off to Washington, is to get them to use multiple data sets from multiple data sources. Let's say your algorithm wants to use Chris and Beers at the same time, or Ayres and Modis, or Modis and Calliope. To get them to assemble that and do it effectively can take them months. It's much easier if we do it here. And furthermore, you know, those of you that have sent code off to Washington know that they like to give you format requirements, they want to give you coding requirements, coding standards. It's got to be in C++ or some other darn language. If you're going to have those requirements, they can be developed here and they can make sense, they can be useful. And I'm convinced that it'll be cheaper for the government. Rather than paying, you know, $500,000 for each person that's a Raytheon contractor or a Harris contractor, they can pay much more reasonable rates here. So if we're going to implement this sort of processing paradigm here, I already talked about you need hardware and storage to do that. But I also mentioned that we've got a finite amount of space to do that sort of thing. Which gets me to another trend that I think we're going to be looking at pretty closely in the near future is cloud computing. And the question really boils down to, do you really want or need to build your own cluster, your own Linux cluster, like a Zara or an S4 or a PEAT cluster? And some of the PEAT team were at the AGU meeting last week, and one of the people that was at the conference came up to them and said to Steve Dutcher, basically, wow, you guys built your own clusters. Like you're superheroes because you know how to put all that hardware together and make it work efficiently. This was a group of people who use clusters but don't build them. They rent them. So you can rent a cluster, or you can rent one server from Amazon Web Services, for example, for as little as 6.5 cents per core per hour. So if you then want to spin up a new server on Amazon Web Services, you can do it through a web GUI. I've done it myself, so it must be easy in less than a minute. And it's not that much harder than actually ordering a book to be delivered from Amazon to your home. Furthermore, if you want to spin up a cluster, a grid engine cluster, very similar to the ones that we have here at Space Science, you can do that in 10 minutes in 10 minutes from start to having the cluster running using a tool like MIT Star Cluster. It's an open source toolkit that essentially you configure what kind of cluster you want to build, how many nodes, how much memory, etc. Tell it go, it'll set that cluster up, install Grid Engine, and tell you when it's ready to use. You can then submit jobs to it. And there's a number of different software solutions that you can use for doing things like that. Now, who uses Amazon Web Services that, is doing a good job, that's, has a high public profile? Well, Netflix runs all their infrastructure on Amazon Web Services. So does Dropbox. So does Instagram. And those are pretty well-known outfits. They have a lot of high performance needs, and they're able to get what they need done in Amazon. Now, Amazon is not probably a perfect solution, but what I've found is that, at least from my reading, I haven't done too much experimenting just yet, is that whatever kind of service it is you want, they probably offer a way to do it. And furthermore, there's different regions within the United States, South America, Asia, Europe, Australia, where you can actually rent their servers. And as part of an investigation I was doing for the Storm project last week, I actually rented a server in Singapore to do some experiments. And it cost me about 50 cents to do what I needed to do. So those are commercial outfits. Well, who cares? We're a space science outfit. Well, there's another outfit that you might have heard of called JPL, and they actually run their Mars public web infrastructure on Amazon Web Services. And running a web infrastructure is one thing, but it turns out JPL actually does processing of their Mars data in Amazon Web Services. I don't know if you remember, but a little while ago they published this sort of high-resolution image of that new Mars rover, an image of itself. So the camera was like sitting out on the arm, taking a picture of the rover, and they stitched it all together. That sort of processing they actually do on Amazon Web Services. And there's actually a couple of nice presentations online by the CTO of JPL, where he talks about how they're using Amazon Web Services at JPL. And how they deal with things like security, government requirements for security, all that business that can make life complicated. But those are big organizations. I think actually some of the more interesting bang for the buck is when smaller organizations or even individuals use Amazon Web Services, because it's sort of a force multiplier. One person can rent, or a small group can rent a lot of resources temporarily on that system, do a lot of work, and then turn it off, and then you're done paying for it. So one use case that I can imagine or envision for what we do here is that we have a core set of servers in-house, or they could be in Amazon for doing routine daily processing. But when you want to do reprocessing, you could spin up 500, 1,000, 2,000, 5,000 servers on Amazon. Do what you need to do really quickly, save the results. Typically the results have much lower data volume than, on output than they did on input, and then shut them all down and you're done with them. You don't have to worry about putting them on the loading dock when their lifetime runs out. So what it means is that there's less work on things like purchasing, installation, the setup, the maintenance, changing out bad disk drives, disposal when you're done with them. And more work can be put in on the daily and the climate data processing. Now, I don't want to make it sound like you don't need IT support to run these things, because you absolutely do. You don't want the scientists interacting with these things directly, other than SSH to log in, which we typically do these days. You still need software people that can install the right applications, configure the relational databases, to set up all the infrastructure to process that data really quickly. And believe me, that's as important a service as the actual development of the algorithms. But then another use case involves this lady right here. And you might ask yourself, what is she doing? Is she checking Facebook? Is she tweeting somebody? Well, actually what she's doing is analysing 10 years of Aquamotus data for a PhD. About 130 terabytes of input data. And let's say that she's smart and she's figured out an algorithm that runs on Modus 1 kilometre data in about 10 seconds per granule. Okay, so how much would she need to spend to get this job done on Amazon? Using tools including her laptop, Wi-Fi, Python programming, and Amazon Web Services. Okay, how much would it cost? Well, I'd annual equals 2,920 runtime hours. The sort of minimal instance on Amazon is 6.5 cents per hour. If you multiply it out, you get less than 200 bucks. So you can do a lot really quickly and really cheaply if you're a smart programmer or a smart algorithm developer. You don't need to buy a huge cluster. You don't need to invest a lot in infrastructure if you're smart. So if you can imagine all the smart folks that are out there, not just in the United States, but in India, in China, and they have a laptop, and they have Wi-Fi, and they know Python, and they know where to get data, there's a lot of interesting stuff that's going to happen very soon. We should be on the forefront of that, I think. So in summary, I'm convinced that we're actually going to be tasked and funded to do large-scale data processing routinely, in the sense that we do it operationally day to day, we do long-term reprocessing. I think we're going to be funded to do that in about the next 2 years, and I think it's going to be to the tune of about 3 to 5 million per year. And I think NASA is going to be a major contributor to that. We'll be doing both LEO and GEO satellites. And these are some of the instruments that we'll be using, that we'll be working together. And we saw a great example of a common algorithm that Elizabeth and Nadia have developed in conjunction with Bill Smith that does AIRS, EARSI, and CRIS. Same algorithm, different sensors. That's also, I'm convinced, the way of the future. And we've also got ClaberX, which does AVHR and Lotus Vias. And I'm sure we have other examples as well. However, the expertise, both on the science side and on the computing side, is all going to be in-house in our building. Or maybe we'll even have a new one. And furthermore, the hardware, the compute, and the storage, it may or may not be in-house. And the point is, it doesn't really matter, because what you really need to access it is a laptop and Wi-Fi. That's it. Thanks, folks.
Well, that's interesting. Yes, Alan.
It's my lucky day. I had enough water to sleep. Anything goes with the day. Enjoy very much. Two quick questions. But I'm pretty sure we are going to try the cloud. We convinced the cloud is ready to go at least. Use that technology. Yes, now. So two questions. The long-term archive security. What's your view? The other thing is, are we pushing responsibility for the distribution of the data? I talk about large bodies of data to the cloud infrastructure rather than our infrastructure. That's cost effective.
Whether it's or not it's cost effective is going to depend on the use case. How much data, how often it's pulled out of the cloud, because it turns out to go into Amazon Web Services is free, but when you take it out, you pay. Now, one way that you would pay for that is you pass that charge on to either your funding agency or to the people who are using the data. But it's going to depend on what kind of data, how often it's accessed. As far as long-term archive security, there's nothing magic about using servers in the cloud in of themselves. When we have servers in 6th floor, we've got to worry about data security. And how do we guard against RAID failures or mechanical failures of disk drives, or the server room gets flooded because one of the cooling water pipes breaks overhead. So you've got to make your own plans to make sure that you have either, you don't maintain the only copy of that data that exists. You know that somewhere at NASA or NOAA there's a backup, and we just have a copy of it here. Or if you do have the only copy, or it's really valuable data, then you've got to make plans to have it stored in 2 different places. So there's nothing particularly magic about it in that sense. You still have to do your own due diligence to make sure things are done safely and securely. And for any particular use case, you'd have to figure out, well, I think I'm going to use this many CPU hours, this much storage, this much data transfer. What's the cost going to be per month? Brad?
I'm really, really happy to hear that all the capabilities that have been developed, particularly at the peak for these climate data records, that you're talking about a future where this is applied to real time. Because I do think there's capabilities here that don't exist anywhere else, and that really does open up a future. One thing that I would like your comments on is
Yeah, I'm well aware of that. However, what I've heard from program managers at NASA in the last couple of years is they're moving away a little bit from this idea, well, that's the DAC's job, and the DAC is the only place that can do that. They're much more interested in the fact that, or in the idea that if NASA has data, anybody needs to be able to get it. And what I see happening on the NASA side, at least, is that we become, partner isn't probably the right word, but a satellite or a mini DAC, not mini DAC, but something like the DAC. I mean, we do a specific part of the job for NASA satellite science, which might be atmosphere and cloud products. Ocean products happen to be done at Goddard. Land products happen to be done maybe at USGS. And what I heard one of the NASA managers say, well, does that mean that you're each going to have a copy of the whole notice archive? And then the light went off in her head that that's okay. And that's a good thing, actually. That's a really good thing. Because you've got it stored in one place that's like a deep archive at Goddard, but it's kind of slow to get it in, kind of hard to get it out again. But you've also got it spread around at 2 or 3 different places that can do their own thing independently with some coordination and do it effectively. So I think, I can't speak for NOAA really because I haven't got too far yet with them, but on the NOAA side, I know there's at least one system that they have by the name of IDPS that's seen as very expensive, not very effective, not very efficient, and they're probably looking for ways out of that contract. And maybe by the time 3 or 4 years rolls around, we'll have demonstrated that, you know, there's an easy way, a more cost-effective way to do that, and have some of that processing done at remote centers, including space science.
I think demonstrating it now so that they see it when they need it.
Well, I think on the NASA side, the demonstration part is almost done, and we're about to move to the operational phase.
Right.
NOAA might follow a couple of years behind.
So the other thing I can comment on, I think your paradigm for the cloud computing, it does work for satellite retrievals because there's a data reduction, lots of data in, less data out. That fake data that's generated by models is the exact opposite. It's little data in, lots of data out, and I think we need to think about how we support modeling infrastructure as well. We start out with initial condition and do a forecast, so we end up with more data.
Yeah, I don't know the solution to that particular issue, but I can tell you that, I mean, you can build something that's very like a Zara, sorry, not a Zara, an S4 in Amazon Web Services today. No problem. Then you have to figure out, well, how do I get data into it? What data do I store? What data do I want to get out of it? But all the hardware infrastructure to do that is available. It's just going to cost you.
Question? June? Yep.
Yes, I'm very impressed about the large volume, increase the volume of data and the sensor agility processing of data. So my question is, in your slide, it looks like we are going to include many things, quite ambitious, like because we are not operational center, we deal with data archiving, receiving, algorithm, and real-time process, the reprocess. That's kind of lots of work. And how do you decide the priority when it comes to them all? Like for example, do we need to archive all the data, or like we just select some based on priority, or like? Obviously looks like if you want to do everything, looks like it's quite ambitious.
It is quite ambitious.
But you were supposed to be.
But it was my job today. Yeah, I mean, I guess I feel like we don't need to think that we're limited by, well, we can't get a supercomputer, we can't get enough data storage, we can't get enough cores to do this or that. We can, as long as you can get funding to support it from your agency. And our experience on the PEAT project has shown that we put a lot of effort into making all the data that we had ingested available to the public because we were told to do that. So now, people are, when they want to get SUMI NPP data, they're supposed to go to class. But I keep having people tell me, well, We tried going to class, but it's easy to get a review. So at what point do you become operational? I don't know. And frankly, I don't care. Because as long as the customers that I'm serving are happy, that's what matters to me. And the agency that's funding me is happy, that's what I care about. Because I'll get more money to keep doing the same thing. Am I operational? I don't know. What the hell does that mean anyway? I really don't know.
All right. Thanks.